right. Hi, good morning, everyone. Welcome to the AI Vision and Sensor Fusion webinar with Edge Impulse and Himax. I'm Adam Benzian. I work at Edge Impulse, and I'm here to introduce our two speakers today. If you go to the next slide.
Yep.
So I'll introduce CK Su, who's a system engineer at Himax. He's in charge of the WE-I Plus system software and hardware development. And this is CK's email. If you have any questions after the webinar, you can reach out to him. And also Relian from Edge Impulse, who leads our user success engineering team at Edge Impulse. He lives in Paris and is also a very avid surfer. And this is Relian's email. And by the way, CK is in Taipei. So hi everyone, and let's get started. And we'll have also some enough time for Q&A after this webinar. And this webinar will also be recorded and shared later if you want to watch it at a further time. So take it away, CK and Aurelian.
Okay, thank you, Eden. I'm CK from Himax Technology. It's my pleasure to have the opportunity to introduce W1 Plus AI processor. In W1 Plus, we have ARC EM90 DSP, and we have multi-bank memory architecture, XY memory. It will very useful for neural network inference. And we also have image accelerator, motion detection, and 2x2, 5x5 filter, JPEG codec, HOG extraction, and the resampler. With this image accelerator is very useful for computer vision applications. And we also have multi-layer power management architecture. So we will only power the necessary circuit when needed. So that's how we reach ultra low power. And we also have hardware security engine, so we can support security boot and the security communication between SoC. And we also have many peripherals. We have a CMOS sensor, so we can get image from camera to support image application. And we have audio interface PDM I2S, so we can support audio input to support audio applications. And we also have SPI I2C UART PWM GPIO interface. And in W1 Plus, we have internal memory up to 2 megabytes, including program memory and data memory and the system memory. With large system memory, we can support up to VGA image for application. So let's go to next page. Here we show a power measurement use case. It's a TensorFlow Lite for microcontroller person detection example. We implement 1 frame per second. A person detection neural network model, the image size is 96 by 96, and the weight size is 250 kilobytes. It's quite large for the MCU-based applications. And for each inference is 60 million operations. And the user case scenario is 1 frame per second periodical wake up. You can see the waveform. Most of the time, the chip stay in standby mode in very low power state. And each second, it will do the fast boot up and the fast image capturing from camera and doing the inference, then go to standby again. That's why we achieve ultra low power. And the major number, the W1 average power is 2.2 milliwatt with onboard DC to DC. If using internal LDO, it will be 3.7 milliwatt. Because our application focus on ultra low power, so in next page, when we implement a use case, we will measure the power on this board with many power measurement headers. We can measure the core power, IO power, analog power. when we developing and use case scenarios such as periodical wake up, or from the motion detection wake up, or from external PIR wake up, we will measure the core power, IO power, and analog power to ensure we can reach the optimized power, because our focus is on battery powered applications. And for the algorithm developer, in next page, we also developing a highly integrated development board. On this board, user only need a micro USB connector to connect to this board, and you can developing your algorithm on PC. And on this board, we have W1 Plus MCU, and we also have Himax HM0360 AOS VGA camera. And we also have on board FTDI USB to SPI I2C UART bridge, so we can programming the flash through USB cable and get the output metadata and message from the target board. And we also have accelerometer on board and 2 microphones. So we can deploy the TensorFlow Lite microcontroller examples, for all the examples. The basic one is Hello World, and we have a vision, person detection example already there, voice, micro speech, and the vibration application match one. So and we already make the SDK available from GitHub, so the user can access the SDK and deploy, developing your own neural network and deploy it to this board. And in next page, this board already go live on SparkFun, so you can purchase on SparkFun and using the SDK in that page. And also we cooperate with Edge Impulse. Right now, the Edge Impulse system can support this board, so it's very easy to use Edge Impulse's environment to developing and deploy to our developing board. And I think later Aurelian will have a wonderful demonstration for neural network developing. Okay.
Cool. Thank you, CK. So just have a couple of slides before showing you like a nice demonstration using the Himax board that CK just talked about. But briefly to talk about what we do at Edge Impulse. So we have a platform for embedded machine learning. And in general, when people think about machine learning, they think about like huge data centers with tons of GPU. What we are doing here is, instead of doing machine learning like on really big machines, we run directly the inference on devices on the edge. And so we can do that from like very small MCUs, so starting from Cortex M0 Plus up to some CPUs. We don't need that much footprint as well, so as low as a few kilobytes of flash and RAM to be able to run the different models. If you are running image detection, it's going to be a couple of hundred of kilobytes. But we can do that in real time and having very low power inferencing, in particular with the Himax board, which is a very low power one for image classification. And so using the Edge Impulse platform, you can build your model using audio sensors information, images, and any type of time series data. And using data from an accelerometer is one of the example, and which is also supported on the Himax EVB board. So we use the platform to acquire data, train your algorithm, test it, and then deploy it back to your device when you run the inference locally. So using the Edge Impulse platform, so the idea is you can manage the whole embedded machine learning pipeline, going from creating your data set. So you can create your data set in different ways. One is to import the data set you already have. So you can import a data set with images, web files, or using a JSON format to import any type of time series data that you could get from accelerometer, temperature sensors, any type of sensor. And you can also create your data set by connecting a device directly to your project. And I will show you that just after the slide on how to connect the Himax board directly to your project. And once you've acquired data, you can start creating your machine learning model. So that's what we call the impulse. And basically the impulse, most of the time, is going to be a mix of signal processing features. Because in general, by applying some signal processing, you can extract more meaningful and valuable information. For instance, if you think about motion detection using an accelerometer, you will get more valuable information in the frequency domain than in the time domain. So for motion detection use cases in general, we will use a block that we call spectral features that will apply an FFT to extract frequency and power peaks data to feed into the neural network. So the impulse will be a mix of DSP features, neural network, and anomaly detection as well. And once you've created your impulse, you can test your model live on your devices. So you can connect a device directly to the platform, or you can also import a test set directly to your project as well. And once you're happy with the result that you have, you can deploy directly your model to your devices. So we've got different ways. You can create directly a binary for the board that we support. So the Himax being one of them. And you can as well export as a C++ library once you are ready to basically merge your machine learning model within your whole application. And let's switch to the demo. So I think I just need quickly to share a new window. Here it is. So now you should be able to see the Edge Impulse Studio that I'm sharing on the screen. And so I'm going to show you like two different projects. One using image detection, image classification, and another one with audio detection. And so I've got the Himax board with me, and I've created this project some time ago, which is basically doing classification between like a screwdriver and a measuring tape or a ruler. So I've been using that during the lockdown because, as many people, I had to get busy. So I was making some work in my apartment. So moving forward, once you arrive on this on the project dashboard, as you can see on the left side of my screen, you can see like the machine learning pipeline I was mentioning before, going from connecting devices, collecting data, creating your impulse, testing it, and then finally deploying it back to your device. So I'm going to go through the different steps. So here, if I go to devices, you can see like I've connected the one Himax board a bit earlier today. And as I was saying just before, you've got different ways to capture data. So if you have an existing data set, you can already like import it directly to your project. You can connect a device directly to your project. And we've got also very cool other ways, such as using your mobile phone. So you can also use your mobile phone and scan a QR code. Like if you don't have any access to any hardware, it's like a very quick way to create a model and getting access to the sensors from your mobile phone, such as the accelerometer, the camera, or the microphone. But in our case, what we are doing is we are connecting directly a fully supported development board to the platform. And so when I click on this link, it basically gets you to the documentation on the Edge Impulse website. So we've got lots of good documentation and tutorials, videos. So I really recommend you, if you want to start working on Edge Impulse projects, to look at the documentation. We really try to make it easy for everyone to get started. And basically, so we've got a section for the Himax board, which tells you what to do to get started. And you can, from here, download the Edge Impulse firmware that will allow you to connect the board to your Edge Impulse Studio. And so this firmware is also available as open source. So if you go on GitHub, you will be able to access it as well. So I'm going to connect my board. I'm not sure if you can see the terminal that I have right now that I'm sharing, but I'm using the Edge Impulse CLI to connect the board to this particular project. And we should see it being connected really soon. Here we are. So now you can see my Himax board is detected and connected to my image classification project. And so once I've done that, like I can go to the data acquisition. So here you can see that I've already collected different samples for my projects, like images of a screwdriver, images of the measuring tape, and so on. But as my camera is connected now, I can do additional pictures. So like I can say, I'm going to capture another picture of my ruler. So I'm just pointing the camera to basically to the table and just click on sampling. And you will see here, we've got the new image that appeared directly here in my project. So it's a really easy way when you have a board which is officially supported by Edge Impulse. You can directly grab sensors data from the device. So in this case, we are using the camera, but we can also use a microphone for audio project or the accelerometer. So once you've collected enough data, so like here for image classification, 30 to 40 images per class will give you like a decent accuracy on the machine learning model. And I see I've got third question from Abhijit. And the third label is basically a random class, which is not a screwdriver or a ruler. So like if I select here the random, you can see like I just took random pictures around in my apartment. And we basically do that to, it's always a good thing to have like an additional class with basically unknown or random pictures. So your neural network will not overfit too much on the object that you're trying to classify. And as you can see here, we have the camera sensors on the Himax is a black and white sensor, which is why you see the images here in black and white. Okay, so now I've collected my data. So moving to the next step, you can have a look here at the impulse that we have created for this image classification project. And the first step you need to do is to basically configure your image input. For image detection, we use something called transfer learning to be able to do image classification. And it is optimized for 96 by 96 pixel images. because we worked with MCU, so it's very small footprint. So the model is optimized for 96 by 96 images. So if you import images that are bigger than that, if they are not square, if they are like high resolution, you just need to select like the resize mode, like if you want to squash, or basically if you want to crop the images that you import. And then we add here an image processing block. And I can show you quickly the different blocks we have. So here we have an image project. So we use this image block, which is basically used to say, like, do you want to use RGB or grayscale for your classification problem? In our case, the Himax sensor is a grayscale sensor. So we are using, of course, grayscale as a parameter for the image. But as you can see here, we've got different other blocks. We'll show you afterwards for the audio. For audio, we've got an FCC, which is really great to recognize human speech, the MFE, and the spectrogram, which is really good in general for non-human voice, non-human audio recognition. Also, spectral analysis, which can be like very useful for motion detection and any type of time series data. And if there is a processing block that is missing because you've got a specific algorithm of your own, you can also add a custom block here and host this block on your server. And then we will be able to point out to your custom block URL and basically run your custom code to extract your specific features. And then finally, my last block is the transfer learning, which we use for images. We've got also like the classic neural network one when you are dealing with other type of data which are not images, and also the anomaly detection block. So moving forward here to image, I can show you basically what we do here. So as I was mentioning, we are doing grayscale. We are not using RGB in this particular case. So not many parameters to tune here for images. And once you've selected the color depth of your images, you've got a nice view here with the feature explorer, which give you a good idea of your image features. If you can define really nice clusters for each of them. And in general, when you have like clusters pretty well defined for all classes, it means that the neural network will be able to have like pretty high accuracy on this machine learning problem. And then you can also like select one by one the different samples and see basically if you may have some mislabeled in your data set. And the last step we have, so as I was mentioning, we use transfer learning, which underneath we use a neural network architecture which is based on MobileNet. So here we use a MobileNet V20035, but you could decide to select a different one. Like if you don't have like much footprint on your device, so like if you have, I don't know, like less than 500 kilobytes of flash available, you may want to use a smaller MobileNet architecture in order to fit it into your particular device. And so the difference is that, so this neural network is basically smaller than the 0.35. So you may need to train on more images or train on more circles, more cycles in order to get a good accuracy. So we just use the default one, 10 training cycles, so default learning rate. We also enable data augmentation, and basically data augmentation, it allows you to add some diversity to your training set. By doing like for images, like flipping the images or adding some noise. So it's a good feature to avoid overfitting of your neural network. And so once you've done that, you can start training. And so you can see here, I'm training it live. I've already trained it before, so you can already see like the performances we have with this particular model. So we had 90.9% accuracy for this particular model. And you can also look at the confusion matrix, which is very useful to check if your model is performing better on some classes compared to other ones. And so here you can see, for instance, for the ruler, the measuring tape, we've got 100% accuracy. But like on the screwdriver, it's only 83. So it might be something worth investigating. Maybe we had some mislabeled, or maybe we had some blurry images, and so it's more difficult for the neural network to establish a classification, a correct classification. And as for the image DSP block, we've got also here a feature explorer. And that's a really cool feature that allows you to see which particular samples, in this case, which particular images have been misclassified. So what you can do is, like I can just uncheck the correct classification. And now I just have the random and screwdriver incorrect classification showing on my 3D graph. And so I can select them one by one. So here I had some random which are not classified correctly. In this case, I would say it's not very important because random, it's not what you're interested in to classify. But like if I look at this one is a screwdriver. And you can see like the image of, oops, yeah, I retrained the network. That's normal. So here you can see like, that's an image of a screwdriver, but the neural network predicted a random class. And it could be because, if I zoom a little here, it could be because like I took as well, like in the picture, you've got also like part of my laptop, which is here. So either maybe I need to get a better image with only the screwdriver, or I need to get more diversity in my data set, which depending on if the objects you try to classify are always in the same locations or different locations, it's important to get as much diversity as possible. So back to our project. So we have trained our model, 90% accuracy. What we can do now is we can try it directly on the board. And here I don't even need to deploy my machine learning model. I just need like the default firmware that we have downloaded previously in order to do the live classification. So basically, the project with the within the Edge Impulse project, I can access to the Himax device that I have, and I can just start sampling as I was doing for data acquisition in order to get a new sample from the camera, and then we will run the classification directly here in my project. And it's interesting, like I got ruler being detected, which is actually correct. But as you can see, like the accuracy is not as good. I mean, it's much better than the other one, so we can be pretty sure that it's a ruler, but it's not like 90, 95% accuracy. And it could be that if I look at my image, it could be because I have basically this band, the black band, which is hanging, and that could be like the reason why the accuracy is not as good as I would expect. So really cool way to use the live classification to see if your model is performing well, and you don't even need to flash your board with your machine learning model to do that. But when you want to do like at a bigger scale, if you want to do testing at a bigger scale, what you would do in general is to acquire a bigger test data set. And from here in model testing, I can select my whole test data set and see on the different samples if I had good classification. So I select, basically I had like 30 images here in my test data set. And you can see I've got 92% accuracy, which is very close to what I had in the training, in my neural network training. So in this case, I would assume that I've got something which is working pretty well. But if you have something which is lower accuracy, you can investigate by selecting like the misclassification. So here, for instance, I've got here the router, which is not, the neural network is not certain about the classification. So I can look at the details of this one. And yeah, this one is classified more like as random. And as before, it could be because of the black band, which is hanging, as you can see on the picture. So we've acquired data, trained the algorithm, the machine learning model, tested it. Now the last step is to deploy. So as I was mentioning at the beginning, you can create like C++ library, an Arduino or WebAssembly when you want to merge your machine learning model within your application. But a very quick way to play with your embedded machine learning project is to build directly a firmware. So here we are dealing with images, and so we are creating image projects. We've got basically two binaries that we can create, one for OpenMV and the one for the Himax. So I select the Himax. I enable our own Eon compiler. It's like really good compiler that allows us to save a lot of space compared to the TensorFlow Lite micro interpreter. So it's always enabled by default, and it doesn't change the accuracy on your model, but it drastically reduces the RAM and ROM usage on target. And the last thing you need to select is if you want to use the quantized version or the float32 version. So float32, it's basically like the neural network weights definition if we use 32 bits or just 8 bits. So in our case, we use a quantized version, and as you can see, we've got actually we've got a better accuracy with the quantized than with the unoptimized one. So we select this one, we click on build, and it will basically load the neural network models that we have created in our infrastructure and build a binary for the board. And now I've got a binary which is available for this particular board. Not sure if you can see my Explorer, but then I've got this Himax directory with flashing commands. So depending if you're on Linux, on Windows, or Mac OS, you can flash the binary on your own operating system. So it works for all operating systems. And once you've done that, so I'm going to share my terminal. Can someone tell me if you can see the terminal which is showing up on top of my screen? Maybe CK, I see your video. Can you just note if you see my terminal or you just see the web browser?
I see web browser and look like a pop-out window is a video file.
Okay, yeah, so you don't see the terminal, so I will share it. So
Yeah, now we see it.
you just see the terminal, right?
Yeah, just the terminal.
Okay. So yeah, sorry for that. Yeah, apparently today I cannot share my whole screen. So I've copied the Himax firmware that we have just created here. And so it's flashed on my board. And now that it's flashed, what I can do is I can run edge impulse, run impulse. And so it contains the machine learning model here. So I've got like here the Himax in front of my webcam. So as you can see here, it's like detecting random because I'm pointing out at my screen. And now I'm going to point to the ruler, which is next to me. And as you can see, like we've got good prediction on the ruler detection. Maybe I can actually do it here in front of my webcam. Yeah, probably it doesn't work really well in front, right? No, it's not too bad. And I can do the same with the screwdriver I have. And so you can see the live classification that I'm doing right now. Let's try again in front of the camera with this screwdriver. Maybe it's not easy because my background is strange. Yeah, it works better on the table. But the idea here is this is like a very quick way when you prototype to use the binary version when you deploy, because you don't need to write any code, and you can just try your machine learning model in the field very quickly. So I think that's all for the image model I wanted to show. I will switch quickly, maybe for 6 minutes, so we have some time for Q&A after. So let me share again my Chrome and switching project. So in this project, what we have done is we have captured like different people saying the sentence "Hello World." So we had different people in the company, different employees who recorded this sentence. In general, using their smartphone. It's like very quick, very easy to do that using your smartphone. And so we've collected roughly 30 minutes of data for this project with people saying the word "Hello World." And we've got also 2 additional classes, one which is unknown. So as for images, this one is basically containing different keywords, different sentences that are not "Hello World." And we also have a noise class, which is basically just random noise, like white noise, that we have captured and added to this project. So different samples that we have captured for this Hello World project. Then here is the impulse design that we have. So compared to the image, the difference here is we are dealing with time series. So we need to select the window we want to use. So we use a sliding window mechanism to do the training and to do classification. And so in this case, we use a 1 second window for the audio. 1 second is like enough, like when you say the word like "Hello World," in general, you will say it in less than 1 second. So that's why we select this 1 second window. And I was mentioning that before already, but we use the MFCC block in this case, which is really great for human speech recognition, and then the neural network block for the classification. So moving to the MFCC block. So here in the MFCC block, you've got different parameters that you can tune. So like if you are familiar with MFCC, you can modify each of those parameters. In most of use cases, it will work really well with the default parameter, but basically the goal of the MFCC is to split your, in this case, the 1 second window in multiple subframes and multiple frequencies in order to extract meaningful features that are very specific to human voice. So we've got the different parameters. We keep the default ones. And here you will be able to see as well the different features that have been generated, like for the images. So like if I, let's say, remove the noise, you can see like between my hello world samples and the unknown samples, we've got pretty much like 2 distinct clusters. So it's basically a good sign, as I was saying, for the image project. It's a good sign that it will work well in the neural network classification. So moving to the neural network. So here we've got a different neural network architecture. So we basically suggest default neural architectures that are different depending on your data set. If you are dealing with images, in general, you will use transfer learning with MobileNet. For audio, like in this one, we will suggest convolutional networks, either a 1D or 2D convolutional network. And for other type of data, like time series data for accelerometer, we will use like a dense network architecture. But if you know about machine learning, you can, of course, like change the architecture that we suggest. So you can move around the different layers, add extra layers, as you can see here. And if you're very familiar with Keras and TensorFlow, you can switch to the Keras mode, like clicking on the 3 dots here, switch to Keras. And then from here, you can directly write the Python code to train your neural network model. So yeah, so I kept the default settings for training cycles, learning rate. I've also added data augmentation. So we also do data augmentation for audio, which, as for images, it's really useful to avoid overfitting and to add diversity to your project. So you can add some noise, mask time bands and frequency bands, and also wrap time axis for it. And then you train your model. And as you can see, here is the accuracy we have for this particular neural network architecture. So it's pretty good, 94.5% accuracy, 94.3% for the hello world itself. And so we've got basically like 4.7% misclassification of the hello words that have been classified as unknown. And so, as I was also saying for the image, the feature explorer here is really useful if you want to check if there are any mislabels, for instance. So like if I just select the incorrect hello word, so I can select each of them. So you won't be able to hear that, but I mean, you can see here the shape of the audio graph, and it's, in this particular case, if I play it here, it's just noise. And our neural network predicted noise, so that's actually correct. So in this case, what you can do is you can say like, view sample, it goes back to the data acquisition page. And here you can say, actually, this was not hello world, but it was noise. And so you just reclassify correctly this particular sample and then retrain again your model. And I could check other one, this one, which this one is just world. So that's why it's not being classified correctly. Okay, and so yeah, as before, so you can test live using the live classification, and you can deploy to create a binary or C++ library. So here, as you can see, I went to select build firmware. We've got more options because we've got additional boards that support audio. But here I select the Himax. And as before, I will flash this this particular model to my board. So it's still creating. And so once we'll have the library, I will flash. Okay, this is good. Building. And so now that I've got my binary created, I can open it. So again, I think I will need to unshare what I have right now. Okay, yeah. So I'm going to share my other screen. I think that's this one. Yes. So as you can see, like I'm flashing the firmware right now on the Himax board. So it may take more or less time depending on the size of your model. Like here, we've got the audio model with 2D convolutional network. If I was doing a project for motion detection, we use like a smaller neural network architecture. So basically, the code generated for my device would be smaller, and it would take less time to flash. So here, yeah, it takes a couple of seconds to flash. And now it's good. Reset. And oh, I need to open a new terminal probably now. Oops. I think I stopped sharing. Sorry. It's back. So I flashed the new model on the board. And so now, as before, I can run edge impulse, run impulse. And this time, it will not look for images as before, but it will look for the hello world. So you see, I was just saying hello world, and we got it classified with 90% accuracy. So like it's running like here every 2 seconds roughly. And if I say again the word hello world, it will detect it one more time. So I got it here. And so by default, when you do the run impulse, it's doing periodic classification, which depending on your application, you may want to do classification like once a minute, once an hour, depending on your specific use case. But sometimes it's very useful to do it like continuously, right? Because you want to do like real-time voice detection. And so what I'm doing now by using the continuous keyword is to run continuous classification. And so now, like if I say hello world, you will see like I got detection here, hello world. I got it here again, hello world. And again. So super easy to do image classification, audio detection. I didn't really have time to show you how to play with the accelerometer, but it is as simple to use the accelerometer from the Himax board. So you can connect the board to your project, start acquiring data. So if you are dealing with motion, you just start capturing, and then you move the board to capture different samples. And same way as for image and audio, you can then deploy your motion detection model back to the Himax board. And that's it.
Cool. So good. Thank you, Aurelian and CK. So I think we can open up for 10 minutes or so for Q&A. So let me actually pick a few questions for you guys. It came a little earlier in the demo. What is the maximum achievable FPS for detection and classification?
That's a good question. So it basically depends on how much time it takes to do the classification. Like when I look at how much time it takes to do prediction on image, it's roughly 130 milliseconds to do classification on one image. So per second, you would be able to achieve 7 to 8 FPS, which is actually really, really good for such a small device.
Okay. Excellent. Let's see. Can you flash two models, I guess, at the same time, or just two models? If it makes sense.
Yeah. No, at the moment, you can flash only one model. The way we have made the SDKs, you can flash one model. But if you, yeah, as I was saying, like all the firmware that we developed are open source. So you could also have a look at how we do basically, how we create the model and run it locally. But in general, it's only one model that you can do at a time.
Okay. Can you run training at an 8-bit mode?
Training in 8-bit, that's a very good question. So when I was showing the neural network settings, as you saw, we have like this quantized version, which is like an 8-bit weight, bit depth. So in this case, we are doing post-training quantization, but we are also working on doing what is called quantized aware training, where basically you could use the 8 bits during the training phase. But for now, it's post-training quantization.
Okay. And there's another question, I think I know the answer, but I'll let you answer. Can you show how you operate the Himax physically? Meaning, do you need anything else like a breadboard, a battery, etc.? I think it's just connected, right?
Yeah, if you see my webcam,
We can see it.
it's just connected to my USB to my MacBook, but that's all. Yeah.
Cool, excellent. And so I want to also tell everybody that we're also available. I'm Adam at edgeimpulse.com. So you can always reach out to me with more questions. And also remind to everybody that you can also purchase this board. Aurelian, maybe if you can go up a couple of slides.
Yeah. Let me.
Spark Fun. So this board is available if you want to try it out and see if this can work for your projects. And they are shipping, I believe, worldwide. So that's also a good place to get started with Himax. And other than that, if there aren't any more questions, oh, there's actually one more question. Oh, there's two more. Is there a way to see the source code of the created firmware image library? It's a good question.
Yes, you can see it if you go on our GitHub. So if you go on github.com/edgeimpulse, just look for Himax, and you will get access to basically to the firmware, the open source firmware that we use. And you can also decide to export otherwise as a C++ to get access to the SDK directly in C++.
Cool, excellent. Another good question. How would you tackle number recognition? For example, getting the reading from an electricity meter. Would that be possible with a Himax board?
Yeah, that's an interesting use case. So like in the case of a meter, you would have like multiple numbers, I guess. So a good way that I see how to do it is to basically like cut your images in subframes. So like you would get one frame for each number. So imagine your meter has like 5 numbers, 5 digits. Then you just cut it in 5 different sub-images, and then you run classification on the different subframes.
Okay, all right. And the last question here is, so is the deployed model just data sent to the generic firmware?
No, actually, when you deploy and you create a binary, it's the full edge impulse firmware that allows you to do data acquisition and running your model as well.
Okay, cool. A couple more good questions. Can I add new data visualization forms or any other SDK to extend, edge impulse?
Sorry, like you said, can you repeat again, Adam?
Yeah, can you add any, say, data visualization forms or any other SDK to work with Edge Impulse? If it's not clear, we can follow up with emails to get more details.
Yeah, visualization. I guess it's like the feature explorer that we had, probably to add something different. So you could do that, like I was mentioning, the custom DSP block that you can use to add your own DSP processing code. And using that, if you look in our documentation, you can also add your own visualization.
Okay, interesting. Another really good question. Can we do bounding box labeling on the images to increase accuracy?
At the moment, we cannot do bounding box for object detection, but it's something we are going to work on.
Okay, cool. Great. So I think that we got all the questions. Thanks for all the nice feedback and questions, and thanks for being here with us today. This will be recorded, and well, it is recorded, so will be shared back. And CK, thank you very much for joining us late in Taipei, and Orlean also a little late-ish in Paris.
That's all right. It's not too,
Hi.
not too late.
No problem at all. So thank you very much, and we'll be in touch soon. Have a good day, good night, everyone.
Thank you. Bye bye.
Thank you. Goodbye, everyone.